Welcome to this comprehensive video on the tangent quotient rule and trigonometric identities. I'm excited to guide you through these fundamental concepts that form the backbone of advanced mathematics. In this video series, we'll explore the fundamental relationship between tangent, sine, and cosine functions. This relationship, shown here as tangent theta equals sine theta divided by cosine theta, is more than just a formula, it's a powerful tool. Understanding these concepts is absolutely crucial for success in calculus, physics, and engineering. These aren't just abstract mathematical ideas, they're practical tools used every day by scientists and engineers. We'll also delve deep into essential trigonometric identities. These mathematical relationships allow us to simplify complex expressions, solve challenging equations, and transform problems into more manageable forms. Throughout this video series, we'll break down each concept step by step with clear visuals and practical examples. By the end, you'll have a solid foundation that will serve you well in advanced mathematics and beyond. We'll start by understanding the geometric foundation of these relationships using the unit circle, then progress through practical applications and problem-solving techniques. Are you ready to master these essential trigonometric concepts? The journey starts now, and I'll be with you every step of the way. Remember, mathematics is about understanding patterns and relationships, and that's exactly what we'll discover together. Now we'll explore two crucial properties of the tangent function: its periodicity and its vertical asymptotes. These properties make the tangent function unique among the trigonometric functions. Unlike sine and cosine, which have a period of 2 pi, the tangent function has a period of pi radians, or 180 degrees. This means that tangent of theta plus pi equals tangent of theta for any angle theta. For example, tangent of 30 degrees plus 180 degrees equals tangent of 210 degrees, which equals tangent of 30 degrees. Similarly, tangent of 45 degrees plus 180 degrees equals tangent of 225 degrees, which equals tangent of 45 degrees. We can prove this using the quotient rule. Tangent of theta plus pi equals sine of theta plus pi divided by cosine of theta plus pi. Using the angle addition formulas, sine of theta plus pi equals negative sine theta, and cosine of theta plus pi equals negative cosine theta. When we divide negative sine theta by negative cosine theta, the negatives cancel out, giving us sine theta over cosine theta, which is tangent theta. The tangent function has vertical asymptotes wherever the cosine function equals 0. This happens because tangent equals sine divided by cosine, and division by 0 is undefined. The general pattern is that asymptotes occur at pi over 2 plus n times pi, where n is any integer. This gives us asymptotes at pi over 2, 3 pi over 2, 5 pi, and so on, as well as negative pi over 2, negative 3 pi, and so forth. To see why asymptotes occur, consider what happens at theta equals pi over 2. At this angle, sine of pi equals 1, but cosine of 2 equals 0. Therefore, tangent of pi over 2 equals 1 divided by 0, which is undefined. This creates a vertical asymptote at this point. The key insight is that as theta approaches pi over 2 from either side, the tangent function approaches positive or negative infinity, creating the characteristic vertical asymptote behavior. To summarize the key properties we've learned, the tangent function has a period of pi radians, or 180 degrees. It has vertical asymptotes at odd multiples of pi over 2, and these asymptotes are caused by the cosine function equaling 0 in the quotient definition of tangent. Understanding these properties is essential for graphing tangent functions and solving trigonometric equations. They help us predict the behavior of the tangent function and identify where it's defined or undefined. Now that we understand what the tangent quotient rule is, let's explore its practical applications. The identity tangent theta equals sine theta over cosine theta is incredibly useful in solving trigonometric problems. This fundamental relationship can be rearranged in 3 different ways, each serving a specific purpose in problem solving. For the first application, we use the formula directly. If we know both sine and cosine of an angle, we simply divide sine by cosine to get tangent. For the second application, we rearrange the formula. Since tangent equals sine over cosine, we can multiply both sides by cosine to get sine equals tangent times cosine. For the third application, we solve for cosine. From tangent equals sine over cosine, we get cosine equals sine divided by tangent. Now let's work through 3 examples to see these applications in action, starting with the most straightforward case. Example 1. Given that sine of theta equals 3/5 and cosine of theta equals 4/5, find tangent of theta. We'll use the tangent quotient rule directly. Tangent of theta equals sine of theta divided by cosine of theta. Now we substitute our known values. Sine theta is 3/5 and cosine theta is 4/5. To divide fractions, we multiply by the reciprocal. 3/5 divided by 4/5 equals 3/5 times 5/4. Multiplying the numerators and denominators, 3 times 5 equals 15, and 5 times 4 equals 20. This gives us 15/20. Finally, we simplify by dividing both numerator and denominator by their greatest common factor, which is 5. 15 divided by 5 is 3, and 20 divided by 5 is 4. Excellent. Now let's move to a more challenging example where we need to find sine when we know tangent and cosine. Example 2. Given that tangent of theta equals 2/3 and cosine of theta equals 3/5, find sine of theta. For this problem, we need to rearrange our tangent quotient rule. Since tangent equals sine over cosine, we can multiply both sides by cosine to get sine equals tangent times cosine. Now we substitute our known values. Tangent theta is 2/3 and cosine theta is 3/5. To multiply fractions, we multiply the numerators together and the denominators together. 2 times 3 equals 6, and 3 times 5 equals 15. We can simplify this fraction by dividing both numerator and denominator by their greatest common factor, which is 3. 6 divided by 3 is 2, and 15 divided by 3 is 5. Perfect. Now for our final and most challenging example, where we'll find cosine and verify our answer using the Pythagorean identity. Example 3. Given that tangent of theta equals 4/3 and sine of theta equals 4/5, find cosine of theta and verify using the Pythagorean identity. This time we need another rearrangement of our tangent quotient rule. Since tangent equals sine over cosine, we can solve for cosine. Cosine equals sine divided by tangent. Now we substitute our values. Sine theta is 4/5 and tangent theta is 4/3. To divide by a fraction, we multiply by its reciprocal. 4/5 divided by 4/3 equals 4/5 times 3/4. Multiplying 4 times 3 equals 12 and 5 times 4 equals 20. This gives us 12/20. Simplifying by dividing both parts by 4, 12 divided by 4 is 3 and 20 divided by 4 is 5. So cosine theta equals 3/5. Now let's verify this answer using the Pythagorean identity. Sine squared plus cosine squared equals 1. We found that sine theta equals 4/5 and cosine theta equals 3/5. Let's substitute these values. 4/5 squared equals 16/25 and 3/5 squared equals 9/25. Adding the fractions, 16 plus 9 equals 25, so we get 25/25, which equals 1. Our answer is verified. These examples demonstrate the power and versatility of the tangent quotient rule. Whether you need to find tangent, sine, or cosine, this fundamental relationship provides the key to solving trigonometric problems efficiently and accurately. Now that we understand the tangent quotient rule, we need to explore a broader and incredibly powerful set of mathematical tools called trigonometric identities. Trigonometric identities are mathematical equalities that involve trigonometric functions. What makes them special is that they are true for all values of the variables, as long as both sides of the equation are mathematically defined. For example, sine squared theta plus cosine squared theta equals 1. This famous Pythagorean identity is true for any angle theta you can imagine, whether it's 30 degrees, 90 degrees, or even negative 200 degrees. But why are these identities so important in mathematics? Trigonometric identities serve several crucial purposes in mathematics and its applications. First, they help us simplify complex trigonometric expressions, making them easier to work with. Second, they are essential tools for solving trigonometric equations, allowing us to find unknown angles or values. Third, they let us rewrite expressions in forms that are more convenient for specific calculations or applications. In calculus, these identities become absolutely essential when finding derivatives and integrals of trigonometric functions. Finally, they appear everywhere in physics, engineering, and signal processing, where trigonometric functions model waves, oscillations, and periodic phenomena. Now, there are many different types of trigonometric identities, each serving specific purposes. We can organize trigonometric identities into two main categories. The fundamental identities include reciprocal, quotient, and Pythagorean identities. The advanced identities include sum and difference formulas, double angle formulas, half-angle formulas, and product-to-sum identities. To see how these identities work in practice, consider this simple example of expression simplification. Here we have the expression sine theta divided by cosine theta. Using the quotient identity, we know that tangent theta equals sine theta divided by cosine theta. So we can instantly simplify this complex-looking fraction into the much simpler tangent function. This is the power of trigonometric identities. In the following sections, we will explore each type of identity in detail, starting with the fundamental reciprocal and quotient identities, then moving on to the powerful Pythagorean identities. Remember, mastering these identities will give you powerful tools for simplifying expressions, solving equations, and succeeding in advanced mathematics. Each identity we study builds upon the others, creating a comprehensive toolkit for working with trigonometric functions. The Pythagorean identities are among the most fundamental and useful trigonometric identities. They connect trigonometric functions through relationships derived from the famous Pythagorean theorem. There are three main Pythagorean identities. The first and most important is sine squared theta plus cosine squared theta equals 1. The second identity states that secant squared theta minus tangent squared theta equals 1. The third identity tells us that cosecant squared theta minus cotangent squared theta equals 1. To understand where these identities come from, we need to look at the unit circle and recall the Pythagorean theorem. In a unit circle, the radius is always equal to 1. When we draw a right triangle from the center to any point on the circle, the horizontal leg has length cosine theta and the vertical leg has length sine theta. By applying the Pythagorean theorem to this right triangle, we get cosine squared theta plus sine squared theta equals 1 squared, which simplifies to our first Pythagorean identity. Now let's see how the other two Pythagorean identities are derived from this fundamental one. To derive the second identity, we start with our fundamental identity, sine squared theta plus cosine squared theta equals 1. We divide every term by cosine squared theta. This gives us sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. Simplifying, we know that sine over cosine is tangent, sine squared over cosine squared is tangent squared. And 1 over cosine is secant, so 1 over cosine squared is secant squared. Rearranging this equation, we get secant squared theta minus tangent squared theta equals 1, which is our second Pythagorean identity. The third identity is derived in a similar way, but this time we divide by sine squared theta instead of cosine squared theta. Starting again with our fundamental identity, we divide every term by sine squared theta this time. This simplifies to 1 plus cotangent squared theta equals cosecant squared theta. Rearranging gives us our third Pythagorean identity. Cosecant squared theta minus cotangent squared theta equals 1. Now that we understand where these identities come from, let's practice using them with some examples. For our first example, we're given that cosine theta equals 3/5, and we need to find sine theta. We start with the fundamental Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Substituting cosine theta equals 3/5, we get sine squared theta plus 3/5 squared equals 1. 3/5 squared equals 9/25. Solving for sine squared theta, we subtract 9/25 from 1, which gives us 16/25. Taking the square root of both sides, sine theta equals plus or minus 4/5. The sign depends on which quadrant theta is in. Let's try a more complex example involving algebraic manipulation. For our second example, we need to simplify the expression, secant squared theta minus 1, all divided by secant squared theta. We recognize that we can use the second Pythagorean identity, secant squared theta minus tangent squared theta equals 1. Rearranging this identity, we get secant squared theta minus 1 equals tangent squared theta. Substituting this into our original expression, we get tangent squared theta divided by secant squared theta. This can be written as tangent squared theta times 1 over secant squared theta. Since secant is 1 over cosine, 1 over secant squared is cosine squared. Finally, since tangent is sine over cosine, we get sine squared over cosine squared times cosine squared, which simplifies to sine squared theta. For our final example, let's solve a trigonometric equation using these identities. For our final example, we need to solve the equation 2 sine squared theta plus 3 cosine theta minus 3 equals 0. We use the Pythagorean identity to replace sine squared theta with 1 minus cosine squared theta. Substituting this into our equation gives us 2 times 1 minus cosine squared theta plus 3 cosine theta minus 3 equals 0. Expanding, we get 2 minus 2 cosine squared theta plus 3 cosine theta minus 3 equals 0. Simplifying, we have negative 2 cosine squared theta plus 3 cosine theta minus 1 equals 0. Multiplying by negative 1, we get 2 cosine squared theta minus 3 cosine theta plus 1 equals 0. This quadratic factors as 2 cosine theta minus 1 times cosine theta minus 1 equals 0. Therefore, cosine theta equals 1/2, or cosine theta equals 1. The Pythagorean identities are powerful tools for solving trigonometric problems. Remember that they all stem from the fundamental relationship sine squared theta plus cosine squared theta equals 1, which comes directly from the Pythagorean theorem applied to the unit circle.